Hello class, this is Ms. Riggins with today's video on section 7.6, non-right triangles. As you're watching the video, don't forget to take down notes, writing down important information, statements, equations, formulas, and graphs. Feel free to pause, rewind, or replay the video as often as you need so you can get a clearer understanding. And at the end of watching the video, go ahead and summarize briefly what the video was about in your notes and submit that summary as well as a top question via the online WISC the day before class. All right, let's begin. So we've been dealing with trigonometry, which is the use and the study of right triangles. But what if we don't have a right triangle? If we don't have a right triangle, how will we be able to determine the unknown side lengths or unknown angles like we can do and determine if we have a right triangle? Well, the way that we can do that is using two very important laws, which you may or may not have heard of before. So let's take a triangle. It's not a right triangle. We don't know for sure. Well, we can't say for sure, but we don't know if any of the angles are right angles. Let's go ahead and label the angles B, C, and I guess this can be A. And then the side across from the angles, the lowercase version of the angle naming. Okay. Well, one of the things is, even though this is not necessarily a right triangle, I can create and make it into two right triangles by dropping a perpendicular from any one of the angles. And what I mean by perpendicular is dropping from a angle a perpendicular line to the opposite side of that angle. In this case, it was from A to the opposite side of A. And when I do that, I break up the triangle into two triangles. We have this yellow this green right triangle, and then this yellow right triangle. And wherever the point where we drop the perpendicular down that hits the opposite side, let that be considered X. And we break up the side across from angle AA into two pieces. The part of length 0 to X and the part from A minus X. Okay? But why is that of any importance? Well, since we do have two right triangles, let's take a look at this right triangle and use Pythagorean theorem to come up with an expression involving this right triangle. Remember, the Pythagorean theorem says that the sum of the squares of the legs is equal to the square of the hypotenuse. So in that case, the leg here is A minus X, and the other leg is H. So when I use the Pythagorean theorem on that, I get this expression. When I just use FOIL or multiply or distribute A minus X times A minus X, I get X squared minus 2AX plus X squared. Okay? All right. That's what I get. Now, if I take a look at this, though, there's something very interesting about this, and that's in the extent of the other triangle, because as you can see, X squared plus H squared, let me have a color. Let me just underline it. X squared plus H squared right here looks to be very familiar. In fact, it is, using Pythagorean theorem on the green triangle, that value is equal to B squared. Okay? And actually, I'm putting it down so we can see this more. Well, if that's the case, then I can rewrite this as A squared plus B squared minus 2AX is equal to C squared. Now, importantly to note is X in terms of the yellow triangle. I don't know if I messed up my colors, but X is involved in the cosine of angle C. It would be adjacent side over hypotenuse. So that means, since cosine of C is equal to X over B, that means that X would be equal to B times cosine of C, which means I can rewrite this as this statement. You can see. And this is the definition of the law of cosines, that for any right triangle with sides A, B, C, and the angle opposite side C, we have this relationship, which is the opposite, and this is how I always remember it. C squared is equal to A squared plus B squared, pretty much like the Pythagorean theorem if it was a right triangle, but then we have to subtract 2 times the product of the legs times the cosine of the angle in between the legs. Yeah, I'll let that marinate on you. And that will apply for not just the hypotenuse, but any of the relationships. I can say that a squared is equal to b squared plus c squared minus 2bc cosine of a. And I can say b squared is equal to a squared plus c squared minus 2ac times cosine of b. So all that applies as well. Now, if you recall, we're talking about angles of a triangle. So A, B, and C are going to be angles less than 180 degrees because their sum has to be equal to 180 degrees. All right, let's look at an example. A person leaving her home walks 5 miles due east and 3 miles northeast. How far has she walked? Well, here's our picture. And as you can see, we don't seem to have a right triangle. But they have given us this angle measurement that this is 135 degrees. Well, I can use the fact of the law of cosines to solve this problem to figure out what C is. So x squared is equal to a squared plus b squared minus 2 times a times b times the cosine of the angle in between the two. And we get that as our answer. Approximately, this should be approximate, okay? All right, what if I don't have all the 3 sides and I need an angle? What if I have just 2 sides and I don't have any of the angles? Then I can't use law of cosines because the law of cosines uses 4 variables, the 3 sides, and one of the angles. So if I don't have at least 3 of the 4 things, then I won't be able to use the law of cosines. So is there another strategy we can use? Yes, there is. So we're using the same exact triangle, but then if we take a look at this, based off this one, let's say this one, the sine of the angle C is equal to h over b, and the sine in the other right triangle of angle B is equal to h over c. So if I solve each of those for h, I get that h is equal to b sine c from over here, and that h is equal to c sine b from the green triangle. Oops, I need to do the green triangle. Sine. Why is that important? Well, they're both equal to h, so therefore they both are equal to each other. So b sine c is equal to c sine b. And so that they can be together with their relatives, we're going to rewrite this such that sine of b and lowercase b are on the same side, and sine of c and lowercase c are on the same side. And we can use that information to find out one of the 4 values. Remember, we have here again, we have 4 values. And in order to determine one of the unknowns, we need 3 of the unknown values to determine that. And we can do that as well. And we can also add in, it doesn't just have to be between B and C, it can also be between A and B. In other words, the sine of the ratio of the angle divided by their side length is going to be the same no matter which angle you're dealing with, as long as they are all in the same triangle. All right, so this is essentially the law of sines, and we're going to take a look at this and solving a problem. The law of sines is better than the law of cosines is when we know a side and an angle opposite it. So here we have an example. Here we have a triangle that's not necessarily a right triangle, and we have an angle and we have 2 side lengths. So if you remember, since this side is 8, then it goes with angle phi, as we can see. And since this side is 7, it goes with the angle across from it, which is the 40 degrees. And we can set up this ratio to solve for the unknown, which in this case is angle phi. And so we get the sine of phi is equal to 87 times sine of 40, which is 0.735. So the big thing is you have to set it up correctly using the angle and the side across from it. Now, a couple things before we end up. Some cases I want to point out is that the law of cosines works when the C is not an acute angle. So it will still work. Just want to FYI. You guys just got to be careful about that. And the second thing is, in law of sines, you evaluate sine of A, but A can be 2 angles because they have the same exact sign. If you recall, if I have a sine of 7.735 and I do inverse sine, sine is positive in the first and the second quadrant. So both of these have a sine of 7.35, but one angle is acute and the other angle is obtuse. So you kind of got to be careful about that, or else you may have used the wrong angle. Okay, so this is a little bit longer than I planned, but I wanted to give you some examples on how to solve the problem. So in this case, that type of problem might have had two answers. All right, that's it.